So in part 2, I'm going to dive into this .geo file and tell you which command line is used to generate or manage the mesh for a particular subregion within the computational domain. Well, this is the 2D cylinder template.geo file we provide you on Canvas. And with this file, you can generate the mesh that is going to be used in Lab 2. In order to figure out and help you understand which command line controls which part of the mesh, I do suggest that you copy all of the template scripts into a new file as a backup. And now go back to your template file. Let's look at the sections one by one. So first of all, let's look at the first part of the script, which is called define the circular cylinder zone. So as the name tells, it should define the circular cylinder wall, which is the exhaust pipe of the truck. So let's just delete all of the rest of the script and only keep this one. Let's actually visualize what kind of thing this part of script does in Gmesh. To do so, first you need to Control S to save the template file and reopen this template file in Gmesh. And you can indeed see that it creates a circular cylinder zone, which represents the exhaust pipe of the truck. In line 12, it says R1 equals 1 to the power of 2, which means that the radius of the cylinder is going to be 1 meter. You might be wondering that in your Lab 2 case, the exhaust pipe has a diameter of 0.081 meter. It doesn't really matter what kind of value you put here. So if I put 1 meter as the radius of the pipe, I can always use the OpenFOAM transform point scale function to scale the circular cylinder down to have a diameter of 0.081 meter. Point 1 defines the origin of the coordinates, and point 2 to point 5 are the basic constituent points of the circle. And then circle 1 to circle 4 connects the basic points and forms the outer line of the circular cylinder. Now let's look at how the boundary layer region is created. So you go back to your backup file, copy this part of the script, and paste it to your template script. Remember to save it before reloading it in your Gmesh. After it is saved, you need to reload the script in your Gmesh. So simply click on Reload Script under Geometry. You can click on Geometry and find it here. And now you can see that our script has been updated after modifying your script. So you can see this extra circular ring, which represents the circular cylinder boundary layer zone. It will have a thickness of 20% the length of the diameter of the cylinder, as I defined here. So basically, the distance between the origin and the outer circle is 1.2 meter here. Again, 0.6 to 0.9 are the 4 basic constituent points used to define the outer circle, and circle 5, circle 8 connects the 4 points to form this outer circle. Additionally, we use 4 lines, so for line 9, 10, 11, and 12 to connect the circular cylinder surface and the outer region. These lines are used to help better smooth transition between different mesh regions, and you will see that later in Lab 2. Remember that in our computational domain, there is a near wall region, which is a square that bounds our boundary layer region. In order to create this square zone, we need to go back to our script and copy this part of the script to our template script. And this will give us the cylinder near-field square zone. To visualize this, save it again and reload it in Gmesh. And we can see this kind of square region outside the boundary layer region. As we defined in line 49, D1 equals 5 meters, which indicates that the side length of the square is going to be 5 meters. And point 10 to point 13 defines the 4 vertices of the square. And again, we'll have this kind of line from line 13 to line 16, connecting the cylinder outer surface to the outer square edges. You might also notice that this edge of the square is not straight line. You can obviously see this kind of curvatures. This is because we are using circles instead of straight lines to bound the square region. This is to help to distribute the cells more evenly across the different zones in your computational domain. To create these circles without letting them have a higher curvature, we are adding reference points far away from the square region, as you can see here. So if you want to create circle 17, it uses point 101 as its center point. So it's far away from your square zone. So we have already finished modeling the most important region in our computational domain. So let's now focus on the rest of the parts in our CD. Let's go back to our script again and copy paste from line 80 to 107. This part is going to define the rectangular domain corners. So it defines the edges of the outer computational domain. So let's save the file and reload the script here. And we can see this part of the code defines the vertices and also the edges of the outer computational domain zone. So how did we define that? In line 85 and 86, we define two length unit. So for line 21, you will see that the x-coordinates of point 21 is minus d1 minus dx. So minus d1 is, as we defined earlier, d1 is 5. So minus 5 minus 10 is going to be minus 15, which means that point 21, so this edge is going to be 15 meters away from the center, from the origin of the coordinates. And similarly, we define a new dx, which is 2.5 times larger than this dx. So it's going to be 12.5 meters. And if we look at, let's say, point 30 again, point 30, so this line is going to be d1 plus dx, so it's 12.5 plus d1. It's going to be 17.5 meters away from the origin of the coordinates. So this edge is going to be further away from the origin of the coordinates compared with the distance between this edge and the center of the origin of coordinates, because we want to give it a larger space to the downstream region where more interesting flow phenomena is going to occur. And now let's try to connect all these points using straight lines. So we did that by copying from line 110 to here to 149 and copy it back to your template script and save it, reload script. So we can see that for line 21 as an example, it connects point 21 and 23. And for line 26 as an example, line 26 here, it connects point 24 and 26. So by using these lines, the outer rectangular region is being bounded by straight lines. And of course, moreover, the outer computational domain has been divided into several subregions. And this is basically the same as the schematic diagram of the computational domain. And so far, our computational domain has already been set up. And now we're going to make the mesh. Okay, so let's look at how we could generate a structured mesh for Lab 2. What we have achieved so far is a computational domain that is considered to be 1D, because our computational domain is only composed of points and lines. But you should note that the mesh could only be generated if the geometry is converted from 1D to 2D. So how could we convert it to 2D? You should simply go back to your backup file and find this part of script here, which is called define surfaces. So we are going to define all these kind of subregions into surfaces in order to convert this 1D case to a 2D computational domain. So let's just copy it and paste it to our template file. Remember to save it and reload the script. So you can see that our computational domain has been updated with some new plain labels added. This means that you have already defined these surfaces by using this kind of script. And now you should be able to generate the mesh. If you go to Gmesh, under Gmesh, you'll find mesh. Sequentially, click on 1D and convert it to 2D. Now you should be able to see some cells, even though they look like they are a bit coarse compared to the mesh that you have down in your lab 1. In order to refine the mesh, we have to define how these kind of points or how these kind of joints are distributed along the edges. To define this point distribution, go back to your backup file again. So copy paste this part of the code, which is named as define point distribution along edges. Copy this part of the code to your template script. Save it and reload script. Sequentially click on 1D and 2D. Now you can see you obtain a much finer grid, even though it still looks a little bit different as the mesh you've done in lab 1, because these cells are in the shape of triangles. And what we want in lab 2 is you could generate structured mesh. So, in other words, the cells should be in the shape of quadrilaterals. To convert this unstructured mesh to structured mesh, go back to your backup file, copy paste this line, these command lines to your GEO template, save it, reload script, 1D, 2D. Now you see with these two command lines, your unstructured mesh has successfully been converted to structured mesh. And indeed, all the cells are in the shape of quadrilaterals. So now we have already obtained the desired type of mesh, which is known as structured mesh. There's another thing before we continue that I would like to draw your attention, is that it is feasible and also very important for you to modify the mesh refinement level in different subregions of the computational domain. For example, if you want to get trustworthy results in your boundary layer region, or let's say predict an accurate flow separation characteristics inside your boundary layer without using wall functions, you really need to make sure that your y plus value equals to 1, which means that you really need to have a very small first cell level height. In other words, you want this kind of refinement lines to distribute more densely or more closer to the cylinder wall. To do so, this could be controlled by your progression number. So if you go to the section called Define Point Distribution Along Edges and find this subsection which controls the refinement in the boundary layer region, which is called the radially from cylinder inner boundary layer, you can find the progression here. So if I want more lines to distribute it closer to my cylinder wall, I can change my current progression of 1.1 to, let's say, 1.5, which is actually a pretty aggressive number. So I save the code, I can reload the script, and 1D, 2D, and now I can indeed see more refinement lines are allocated closer to the cylinder wall, and the first cell height is indeed smaller than the previous case. There's also another way to do this. So instead of using an aggressive progression number of 1.5, let's change it back to 1.1, we can add more refinement lines. Instead of 13, let's say we add 33 refinement lines in the boundary layer region. I save the code, reload script, 1D, 2D, and yeah, it's almost the same. And I indeed have more lines allocated to the cylinder wall, and my cell height is indeed smaller than the original case. So this will help you get a lower Y+. On the other hand, if you want to change the refinement level outside your boundary layer region, so let's use the top vertical region as an example. So if I want to add more horizontal lines inside the top vertical region, I can go to this subsection called top vertical edge going left to right. This basically means horizontal. So I can first add more lines. Instead of adding 21 horizontal lines here, I can add 50 lines. Save it and reload script. And oops, it seems like we indeed added 50 horizontal lines, but most of them are allocated densely at the bottom. So this could be solved by reducing the progression number from, let's say, from 1.105 to 1.005, and it should make my refinement lines to distribute more evenly. So let's reload the script, and indeed, this is what we expected. We get a more evenly distributed refinement lines in the top vertical region. The reasons that I suggest you to modify the refinement levels in different subregions of the computational domain is not only to help you get a desired y plus value inside your boundary layer region, it is also helping you to get a higher quality mesh. So when I say high quality mesh, it means that you need to ensure the transition of mesh refinement levels between different subregions of the computational domain to be as smooth as possible. So for example, as I demonstrated earlier, if I change this back to 50, so I will be adding more horizontal lines in the top vertical region. But you can clearly see these abrupt changes in the mesh refinement levels in these two different subregions. This kind of abrupt changes can really lead to numerical instabilities, such as oscillations, numerical errors, and also convergence issues. And moreover, a smooth transition of the mesh refinement level really helps you to reduce the computational cost of the simulation by minimizing the number of cells required to capture the flow physics accurately. So I do suggest that you play around with this section of the script in your Lab 2 assignment. Just like what I have done in Lab 1, currently what you have obtained now is a 2D mesh, and OpenFOAM can only perform CFD simulations on 3D objects. To convert this 2D mesh to 3D, you can simply extrude this current mesh by 1 unit. So if you go back to your backup script and copy this part of the code and paste it here, save it, and reload script, and you can see our mesh is now 3D, and you can see the thickness is with a span of 1 unit. You can click on 1D, 2D, and now 3D to see these 3D meshes. We are almost there. Before finishing our final mesh generation, we need to define the fluid media inside the computational domain. In your backup code, this section of the code basically defines the volume inside the computational domain as fluid. So copy this code to your template script and save it, reload the script, and sequentially click on 1D, 2D, and also this time 3D, and you have now defined the volume of the computational domain to be fluid. To check this definition, you can go to Tools and then Visibility. You can see that a volume called fluid is being defined inside your computational domain. Click on Apply, and again go to Tools, Options, and toggle this volume, and you can see the fluid distribution inside your computational domain. Another thing, you indeed don't see any fluid distribution inside this circular cylinder, meaning that our pipe is waterproof and this volume definition is successful. Lastly, we need to define the boundary patches. Basically, we need to give the name such as inlet, outlet, top and bottom, front and back to the computational domain as you did in your Lab 1. To do the name assignment, I suggest that you can work directly in the GMesh user interface instead of working in the text editor, because it's much easier and more intuitive to work here. But first of all, let's get rid of all these undesired and annoying point and curve labels by deactivating these selections. I don't really need the volume as well, so let's just get rid of that. If I reload script, and here I got a clearer picture for me to work on. So let's now do the name assignment to the boundary patches. So to do so, click on Physical Groups and find Add and select the Surface option. And here you can add the name to the boundary patches. So let's start from maybe inlet. So you can select the inlet patches inside your computational domain, which is this surface, and this one. After selecting it, click E to end your selection. So you click E and it's done. So if you go back to your text editor, and you should find your script is being updated. So here. So this is these are the surfaces that has been selected just now for your inlet. So we can now do similar to your outlet as well. So for my outlet, it's this surface, and also this one. And I name them as outlet. Click E to end. And here to check, yes, it's being updated. Now I should move on to name the front and back of the computational domain. I will name them as wall. Sorry, I will name them as sides this time. So this is going to be a long process. If you are practicing on your own, you can skip this part, but do remember to treat it with care and don't skip any of the surfaces, which will lead to severe error in your OpenFOAM simulations. Also remember the surface in the square zone as well. Yes, this is the front side. And now we can go to the back. If you accidentally select the wrong edge, you can press U to undo the last selection. Yes, this one. Oh, I've already selected this one. This. And also here. Now it's done. And yes, I think it's all correct. And I will give them a name called sides. I click E and check my script here. And yes, it's being added. Now I need to define the top and bottom for my computational domain. This is the top. And my bottom as well. Define them as top and bottom. Click E to end selection. Yes. And finally, let's define the wall, which is the surface of the cylinder. It should be composed of 4 surfaces. So this one, 2, 3, and 4. Yes, I name them as wall. Click E to end selection. And my wall has been added. So I can click Q to abort. So all the name has been added to the surfaces. You can now check it by going to Tools and again Visibility. And you can see surface inlet, outlet, sides, top and bottom wall has been added to the surface. For example, if you click on inlet and click on apply, and you can only see the inlet. For the side, yes, it's the front and back. Top and bottom is, it's the top and bottom, and the wall is just going to be the cylinder wall. And that is all correct. And that's it. So the mesh has been finished and it should be ready to run in your OpenFOAM. So now you can go back to your mesh. So click on Visibility, click on Tree, and go to the bottom. Find this current model and say Apply. And this is the original mesh you're going to use in your lab too. At the end of the tutorial, I'm going to show you how you can save this mesh and export the mesh to OpenFOAM. Before saving the mesh, click on 1D, 2D, and 3D until you see the mesh shows up on the screen. And this is the mesh that is ready to run on OpenFOAM. To save this mesh, click on File and click on Save Mesh. And this mesh file is going to be saved at the place where the 2D cylinder template.geo file is kept. In the beginning, I put this file in my case folder. So if I go back to my OpenFOAM case folder, I can find a .msh, which is a mesh file being generated by Gmesh just now. Again, you need to convert the mesh file to an OpenFOAM readable file type using OpenFOAM's mesh convert function. In Lab 1, the function was plot 3D to foam, and in Lab 2, it is going to be Gmesh to foam. Let me quickly show you in my Ubuntu terminal. So I first need to go navigate to my case folder, Lab 2, and type Gmesh to foam, followed by the name of the mesh file, .mesh, and click Enter. So now my mesh has been converted to OpenFOAM readable file. You can navigate to your case folder to check, and yes, I have my mesh converted in my Polymesh folder. So my mesh is being converted. Last but not least, just want to draw your attention that you need to remember to rescale your mesh size down so that your cylinder has the desired diameter. Now, our mesh has a cylinder diameter of 2 meters because we set the radius of the cylinder to be 1 meter. So if I want to rescale my mesh size down so that my cylinder has a diameter of 1 meter, I need to run the transform point scale function in OpenFOAM as I mentioned earlier in my tutorial. So in this case, I can do transform point scale followed by the scaling factor on X, Y, and Z axis. Click Enter. And now my mesh has been scaled uniformly by 0.5. I can again visualize my mesh in ParaView to check if my cylinder has the correct size. And now you can see my computational domain, and by clicking surface with edges, you can see my mesh here. If you click on the ruler here and specifying the starting and ending point, so starting from -0.5 to 0.5 along x-axis, click on Apply, and you can see that our diameter of the cylinder is indeed scaled from 2 meters to 1 meter. This is the true end of the Gmesh part of the tutorial. I have covered the basics of using Gmesh to generate a mesh for 2D flow around a circular cylinder. I do recommend that you practice a lot, practice what you have learned, and don't hesitate to reach out to us if you encounter any issues along the way.